All right, let's get started. Welcome, everyone. Good evening. Welcome to another installment of Crossroads of Ideas. I'm Janine Barania. I'm the Senior Director of Intellectual Property and Licensing at WARF. WARF is the Patent and Licensing Office for the University of Wisconsin-Madison. We support the university and the Mortgage Institute for Research by supporting the cycle of innovation where you have research and you have discovery, and then WARF works to protect the technologies and find commercialization partners. So that way we can take these transformative innovations that happen on this campus here and bring them out into the world. So that way people like us can utilize them. Crossroads of Ideas is a collaboration between the Mortgage Institute for Research, the Wisconsin Institutes for Discovery, and WARF. And it is the opportunity to foster a dialogue between the community and researchers here on campus. And it's all about important, unique aspects of research that we all care about that can have impact on our lives, and that there's also this research going on campus. But before I say any more about this evening's event, we'll take a moment to acknowledge the land that we occupy here at the Discovery Building. The University of Wisconsin-Madison occupies ancestral Ho-Chunk land, a place their nation has called Dejope since time immemorial. In an 1832 treaty, the Ho-Chunk were forced to cede this territory. Decades of ethnic cleansing followed when both the federal and state government repeatedly, but unsuccessfully, sought to forcibly remove the Ho-Chunk from Wisconsin. This history of colonization informs our shared future of collaboration and innovation. Today, University of Wisconsin-Madison respects the inherent sovereignty of the Ho-Chunk Nation, along with 11 other First Nations of Wisconsin. Before we hear from this evening's speaker, I have a few housekeeping details. At 7:45, we'll stop and take Q&A. For those here in the room, just walk up to the mic and ask your question. If you're online, please use the Q&A function of Zoom, not the chat, but the Q&A portion. And we'll try to get through as many questions as we can before we'll promptly end at 8. Crossroads has been a staple of the Discovery Connections programming since 2014. The name of Crossroads of Idea reflects the importance of the Discovery Building being here kind of at the center of campus, but also reflects all of the different research disciplines that happens here within the building and the surrounding areas around us. So it's my pleasure tonight to introduce our speaker, Cary Forest. Cary is a professor of physics here at UW-Madison. He is also a Badger alum, receiving his undergraduate degree in applied mathematics, engineering, and physics here. He has a PhD from Princeton in astrophysical sciences and plasma physics. He's received numerous awards here at UW as well as nationally, and he is currently the director of the Wisconsin Plasma Physics Laboratory. His research relates to experimental plasma physics on the border between nuclear fusion and plasma astrophysics. Talking about what he does is just a total tongue twister. I've had the pleasure of working with Professor Forest for a number of years now with his lab and collaborators as they're generating new next generation fusion technologies, including cool things that they've named WHAM that he'll tell us more about this evening. So welcome, Professor Forest.
Okay, you should hear me? Good. Thank you for coming. I'm going to tell you tonight about some things that we're doing in my lab and some new directions that we're taking fusion here in the state. So I initially intended to give you a big history of fusion here at the UW. I'm not going to do so much of that, other than to mention that it's an amazing program I joined in the mid-90s that had its start in the early 60s. It's one of the only places you can do fusion research in the country. The UW has produced 500 or more graduates that have leadership positions all over the world. And I think it's worth acknowledging that as the core strength from which Wisconsin could build in this area. So yeah, you heard my history, a little bit of it, but I might just mention that not only did I grow up here, but that I started my research here, working with Professor Noah Hershkowitz in the engineering physics department. I'm working on the magnetic mirror concept in part, and what I'm talking about today will be closely related to that. I went to Princeton. I started working in tokamaks. I went to a company in San Diego and was very active in advanced tokamak research. It was so exciting at the time in the early 90s. And then about 1996, 97, we were looking at ITER as the next step. And they were saying, so this is a device I'll tell you a little bit about. ITER was going to have its first plasmas in 2016, and it was going to take until 2025 to complete its fusion mission. And in 1996, this looked like it was so far in the future that I became a little bit disinterested and wanted to find something else that was intellectually challenging, which is why I stepped into the astrophysics area. And I sort of remained involved with fusion for a long time, but it took something special to bring me back. And there were sort of three things that brought me back. One is that we were collaborating with some folks in Novosibirsk, Russia, that were presenting some results which were just unbelievable to me, that you could make a simple fusion device operate stably. And I'll talk about that. Another thing that was happening is here in Wisconsin, we had this company Shine, which was making neutrons that for commercial purposes. And it seems like we could sell fusion and make money. And there was a commercial appetite for what we were doing independent of making fusion for energy. And now, there's a huge appetite. And so it seemed like back in the day, there wasn't a big desire to jump into fusion from the country. It wasn't quite ready, but it seemed now things have changed. And then the third thing is there's a whole new generation of technology, and the technology I'm most interested in is the newest generation of high temperature superconductors that allow us to build magnetic confinement machines with magnetic fields that are much stronger than was possible. And that is what brought me back. And so I've been working in fusion now for about really actively pushing this concept for the last 5 to 10 years or so. Okay, so here's roughly an outline. Let me just start with some fusion in the news, and then I'll give you a brief reminder of what fusion is, very basic, just to remind you why fusion energy is interesting. And then I'm going to talk about the UW research we're doing and the company that is spun out of that with WARF's cooperation, Realta. Realta is the word for star in Gaelic, and so we're trying to build a star on Earth, and that's and we have a path to fusion that I'll tell you about. So you, maybe everybody who has not seen any of these articles. Well, so three big things have happened in the last 2 years, several years. One is that there's a company in Boston, and can I point? I have to probably point with the pointer here for those online. So there's a company that spun out of MIT that has been using these high temperature superconducting magnets to build very strong magnets for a device called the tokamak. And this made the national news last year, and it led to a $2 billion raise for their company that then is spun out of that. So this is a big deal. The experiment in England that is sort of the precursor to ITER, the so-called JET experiment, the Joint European Torus, revisited doing experiments with tritium, the fuel that is needed for fusion, and they beat some records by making much longer pulses at pretty close to unity gain. And then finally, just in the last year or so, we've seen an inertially confined plasma, lasers being used to ignite essentially a small nuclear weapon, burn and produce net energy gain. And so this has been pretty exciting. And it's led to a lot of interest from the private side of things. And so there are a number of startups that I think the current counting is something like 30 startups in fusion energy that are operating, and many of them are very well funded at this stage. And so here are three. Here are three. And even here in Wisconsin, I'll tell you about our startup, but there's also another startup that's working on a concept called Accelerator Type 1 Energy, and they just announced a big raise a couple of weeks ago. And so this is very exciting, especially since it's here in Wisconsin. So the problem we're working on, as I'm not going to talk too much about it, except at the end if I have some extra time, is we need energy. We need lots of energy. Our quality of life is related to energy, and we need energy that doesn't emit carbon. We can't get by, we have to solve this problem. And fusion is a good solution to that. So what's fusion? Well, fusion is the energy source that powers the stars. it's a nuclear reaction that takes two isotopes of fusion. So deuterium is a proton plus a nucleon. So this would be a component of heavy water. This is slightly, a regular water would be built up of hydrogen protons around oxygen. But if you add a neutron to that nucleus, it becomes deuterium. Tritium is two neutrons plus a proton. And if you bring these two things together, which requires a lot of energy to push them to overcome the charge that's pushing them apart, you can get a nuclear fusion reaction, and that can create helium and a neutron that carry lots of energy. So if you add up the rest masses of the deuterium and tritium, and you added up the rest masses of the helium and the neutrons, you'd find that the helium and the neutron weighed less. And that energy is the converting the energy of mass into energy just via Einstein's formula. So that's what fusion is. There's a lot of fuel on Earth that would essentially be endless as far as we're concerned. There's lots of deuterium in the ocean. If we had a fusion power plant producing about 1 gigawatt of power, you need to cycle through about 30 tons of seawater a day to extract the deuterium that goes into that. There isn't any tritium found on Earth. You somehow have to breed this. We can breed it using a neutron, which comes out of fusion, and lithium. And lithium we can then get tritium from that through this reaction here. And there's enough lithium-6, that's an isotope, for 1,000 years plus of energy usage here on the planet. So fuel seems to be abundant. And again, so the problem is these nuclei, when you try to smash them together, they don't want to come together. The electric force between them forces them away. And so the problem is you need to give them an enormous amount of energy in order for them to overcome that barrier. And what this means is that you need to make a gas that's extremely hot. And so I have a temperature down here in keV. I should have plotted this this is 100 million degrees Kelvin. And the reaction rate for DT fusion is optimized at about 100 million degrees. And that's a very, very, very hot gas. The center of the sun is much colder than that because it's huge. It doesn't need those high temperatures. So what conditions are needed? So to make fusion in the lab, you need a very high density plasma. We talk about density in terms of the number of particles per cubic meter. So this is about 1/100,000th of the density of air. So it's almost a vacuum, but it's still pretty dense. But we need a very, very high temperature gas. So this is something like air at 1 million times the temperature of the room. And we need to hold it in place long enough. And you can form a triple product from these three things: the density times the temperature times the confinement time, which is something that needs to be large enough for fusion to happen. And this has been worked on by a lot of people, but we know approximately what the conditions are that are needed in the lab. And it needs to be denser and hotter and be held better than we know how to do at the moment. There are three approaches to fusion energy that I know of. One is gravitational confinement. We just put enough hydrogen in one place that it forms a star. It compresses and heats up, and it burns. And this burns, very, very, very slowly. Fortunately for us, it burns slowly enough that the sun's going to be around for a long time. Another way to make fusion happen, and this is the inertial confinement approach, is to use lasers to make a very hot X-ray gas that can compress a small pellet of fuel. And that's essentially how a nuclear weapon works. And we know that works because nuclear weapons work. And so that's how laser fusion or inertial confinement work. And then finally, what I work on is using magnetic fields to confine plasma. So if you have a magnetic field, the particles tend to gyrate around the magnetic field due to their Lorentz force in tight little beads, tight little circles. And they're free to stream along the magnetic field, but it's very hard for them to move across the magnetic field. So you might say, well, that sounds great. The problem is that somewhere magnetic fields often touch some surface. And so if you try to make a plasma hot and you have a magnetic field that touches some wall somewhere, it's going to cool off and it gets very hard to make the high temperatures. So early on, people had the great idea, well, why don't we just take the magnetic field and turn it in a circle and close on itself so that there's, the particles are free to move around the wire, if you will, but not free to move across. And that works. That's what's called toroidal confinement. The problem there is that it's complicated. You have to build magnets that are toroidal, donut-shaped in character, and there are many issues that have to be dealt with in order for that confinement to work. And so we'll be talking about something different here. Nonetheless, there's been enormous progress over the last 50 years. And I'm just showing here that between the mid 60s and 2000 or so, there was this steady progress in that triple product that just increased faster than Moore's law, the thing which governs how fast computers were improving with time. And the problem is that in about 2000, this petered out. The experiments became too big to build in a short period of time, and we couldn't yet field the next device. As I said, there's an ITER is an experiment that's slated to operate later this decade, and it took over 30 years to build from conception. Of course, that's not all of it. You also, in order to make energy, you need a lot more than just the fusion engine. You also need a way of extracting the heat. Heat comes out mostly as neutrons. It gets collected in a blanket that can breathe the tritium. And then the heat that's left over, we send through a turbine and create electricity. So this is a big challenge, but it's a great solution if we can get it to work. We have lots of hydrogen. There are no long-lived radioactive wastes if you build the machine correctly. There's no chance of a runaway meltdown type of reaction. And I think its time has come because of a lot of advances that have been made recently. However, we're still waiting for net energy production. And the problem might just be that fusion so far is just too big to scale. And this is a picture of the ITER device that was conceived of in 1986 in the Gorbachev-Reagan meetings. And so from conception to first plasma is going to have been over 40 years. It's an enormous plant. The actual Taurus Hall, which I think I can find it if I looked hard, but it's almost lost in the physical plant. And so this is a challenge. Okay, so why is now the time? You can see that this doesn't look so good. So why is this our Kitty Hawk moment? And there are a couple of things that make this a special time. The first are these high temperature superconducting magnets that I was telling you about. The big breakthroughs in the solid state physics were in the early 90s, I believe. But it took a long time in order to turn that into a technology which could be used to make magnets. And it's only in about the last decade that we've started building actual magnets with these materials. And the fact that we can use stronger magnets means we can build smaller, more compact machines. And in principle, this speeds up the time scale and reduces the cost. The second thing that's happened is we have incredible computational power now. The computers have become so powerful that we can put trillions of particles into a computer and simulate how plasmas would behave and design, if you will, in silicon, the future reactors. And so this is a big deal. Also, just processing power, just the sheer ability to feed back on plasmas and make them stable has gotten better and better because we have signal processing that's sped up. We also have semiconductors that are more capable of putting out lots of power. And there have been some massive advances. I'm not going to go into great detail on these on experimental progress. So in about 7 years ago, the first big results came out of this mirror concept I'll show you in a second, the gas dynamic trap in Russia that we were working with. And they also were able to measure an electron temperature, which was at the level that tokamaks made their breakout move in the late 60s. And so there was a moment when tokamaks reached 10 million degrees, and that made them the preferred technique for going forward with fusion. So all of these advances have been made, and that's what we're up to. Okay, so I'm not going I think I won't go into this. So our conjecture is we can start with something, that we can certainly build at this point. We have the scientific capacity for building something like ITER. And this is being built now. It's 20 to 40 billion dollars, depending on how you account it. And it's 30 plus years to build. It's a company in Boston now, Commonwealth Fusion Systems, which is very active right now. They're working with these high temperature superconducting magnets, allows them to make the magnetic field stronger by at least a factor of 2 in the middle. And this is allowing them to reduce the size of the experiment. And with the same physics basis, they're able to, they think they'll be able to build a device that ignites and makes a burning plasma at about 1/10 the cost, maybe even less than that. And this is still a toroidal system. And so our conjecture, the reason we got started on this was, well, could we take these same advances now in the high temperature superconductors, build a much simpler device called a magnetic mirror, which isn't a torus, it isn't a donut. It suffers from this problem of open field lines touching walls and all of that, but it's so much simpler. It's just 2 planar circular coils that make the confining magnetic field. And that plus the high field magnets, the simplicity plus the high field magnets allows us to build, in principle, a break-even experiment at maybe 1/10 the cost of what we can do with CFS. And this is our ambitious goal, and we're trying to figure out if we can do this. So this is the concept. So this is a magnetic mirror. The blue parts are the superconducting magnets inside cryostats. They're very cold cryogenic temperatures, but they're just 2 magnets, 2 very simple magnets. And in between, there's a weaker magnetic field, and particles bounce back and forth between the high field magnets at each end, and that provides the confinement. So the particles, they are reflected, and that's why we call it a mirror. So it's like the particles are reflecting, not light in that sense. And we took this concept. We thought it might work. We applied to the ARPA-E agency that's part of DOE, which is willing to take risks that the rest of DOE is not necessarily willing to do. And we got lucky. We got a big grant. $10 to $15 million later, we built a prototype experiment down in Stoughton at the Physical Sciences Lab. And it has a mission. Its primary mission is to show we can make plasmas with these HTS magnets and replicate at some level the results from Russia. We teamed with Commonwealth Fusion Systems to build these high field magnets. So here's one of them. They named them Thing 1 and Thing 2 after the Dr. Seuss characters. And Thing 1 was doing great until we pushed, we're trying to get 17 Tesla in the middle, and we pushed to 16.2, and then it broke. And we figured out why it broke, and we rebuilt it, and we're about to test it again. And Thing 2 is just about to be delivered. And so we're expecting these now this spring and hope to have our first plasmas in the summer. And many of you have probably been down to the Physical Sciences Laboratory in near Stoughton. There was a synchrotron down there for a long time. We're now occupying one end of that laboratory, and this is sort of our lab over the last 2 years. And one thing so you can see the vacuum vessel has just been put in the middle there, the silver thing, and the 2 stands. And you can see this is relatively easy to assemble. It's just a long cylindrical system. We have pieces that we can sort of drop in place. And right now we're waiting for the 2 magnets that will get dropped in between these sections. So there's a central section where most of the fusion's happening, and these big end bells where the plasma is spread out and dissipated over a large surface area. And we can use those ends to also control things. We have a neutral particle accelerator here. That injects about 1 megawatt of neutral atoms that are able to get across the magnetic field and fuel the inside of the machine. We have some very high-powered, very high-frequency microwaves, about 50 times the frequency of your microwave oven, so very short wavelength, and that's about 1 megawatt of power also that goes in and can resonate with the electrons that are spinning around the magnetic field and heat them up to a very high temperature. So This is the lab. This is what we call WAM, and WAM stands for the Wisconsin HTS axisymmetric mirror. And so it's basically simple circular coils that makes it axisymmetric. HTS is the high temperature superconducting magnets, and it's a mirror configuration. So as we were going through this process for the last couple of years, I sort of feel like I've been inventor in chief for the project, and we've been trying to write down the ideas that we think are unique and special, working with WARF to get them turned into patents that would be useful. And we have been quite successful, I think, with some good ideas. ARPA-E, our headmasters, had another task for us, which was you have to come up with a commercial plan for how you're going to turn all of this stuff you're doing with our money into something useful. And they said, you really need to develop a commercialization plan. And I scratched my head and said, I don't know how to do that. Janine, can you help me do that? Is there somebody you know that would be able to help us do that? And she put us in touch with Karen Furlong, who is a business type that has been in the startup world, and we've tried to figure out if we could work together. And one thing led to another, and eventually we were spinning out this company, Realta Fusion, which is an early stage startup. It's founded, we officially incorporated last November, and we're making a lot of good progress. So Realta Fusion is the company. We are pursuing the magnetic mirror because it's simple. We think it's the simplest, cheapest, most direct way to fusion. And we're targeting industrial heat rather than electricity generation as a first step. And really that's because most of the energy that's used in the world is used for making things, not moving things. And if you're going to have an impact, you have to be working on attacking, the four pillars of civilization, which are cement and steel and fertilizer and plastics. Those are the things that eat up most of the energy that we need. So that's our plan. And our slogan is simpler, cheaper, and faster. This is all fun for me because I'm mostly an academic and I'm not getting used to the sales pitches, but we're working on it. So this is the mirror in movie form, and just to show you, we've got two big magnets that we energize. We inject plasma into the middle. It streams out to the ends. And one really cool thing about this, so here you can just see these are what the orbits of the fast ions that are doing the fusion do. They bounce back and forth, and that's what gives the confinement. One very interesting thing is that most of the energy leaks out the ends, and the plasma comes out the ends as basically a very high velocity, it's a rocket exhaust out these little nozzles. It kind of looks like a rocket. And all the energy is contained in the kinetic energy of the massive ions. The electrons don't have much kinetic energy. So what we do is we strip the electrons out of that stream, and then we can collect the current of ions directly as DC power and convert the plasma losses back into electricity in a direct way without having to go through a steam turbine cycle. And this is a big advantage of the mirror. We have a direct conversion mechanism for taking the charge particle fusion energy and turning it straight back into electricity, recycling it in the middle. And this improves our game, right? If we recycle 80% of the power that's lost out the ends that we were having to put in to keep it hot, we've increased our fusion gain by a factor of 5. So our break-even conditions become a little bit simpler in that way. So, if this is so simple, hasn't it been tried before? And what didn't work? Well, it is a mature concept, but I'll tell you some of the reasons why things have changed. So this is a database from the early 70s from simple mirrors like I'm showing. And it is, back in the day, they didn't know how to make simple axisymmetric mirrors stable. They had to make magnets that were quite complicated in shape. So the currents in this magnet, they're shaped like the seam of a baseball. And this makes a magnetic field which is it has no axis of symmetry, but it has a strong field at one end, it's weaker in the middle, strong at the other, but the plasma is stable, it doesn't bubble out. The magnetic field gets stronger everywhere as you move outward, and it was the way that they dealt with making the plasma stable. And during that time, they were able to show that in this device, by increasing the temperature of the ions, the fuel, and going to 10 million degrees or so, the confinement basically agreed with theory. This almost never happens. And it just got better and better, and validated that as the ions became less and less collisional, they were better and better confined. And this is a remarkably good scaling for fusion, right? As you make your fuel hotter and hotter, it gets better confined. And this was established. But at that time, when they looked at it and where it went, this scaling law for the device they had built didn't reach break even. So break even is the point where the fusion energy that comes out is equal to the heating power you're putting in. The dotted line up in the corner there is the region where you'd get break even. You want to be beyond break even to make net energy. But the line that they had at that time didn't get there. And the concept was more or less abandoned at that time because it just wasn't going to work. And one of the reasons it wasn't going to work was because the mirror ratio, so the mirror ratio is the ratio of the strongest field to the weakest field, was limited to about 2, okay, because of this baseball-shaped coil. Another thing was they couldn't make magnetic fields which were strong enough to hold the dense plasmas in this configuration because of the shape. And so we can now, we believe, following the Russians, move this curve up and to the left onto the green curve, because we can make a much higher mirror ratio. So we can use very, very strong magnets at each end and a weak magnetic field in the middle, and this improves the overall overall fusion capacity. And so this makes a denser, hotter plasma and moves us into the upper right-hand corner where fusion happens. So this is density times confinement time, and this is the ion energy, and we want to be up in the green here for fusion to happen. They didn't give up in the 70s. So there are these results coming which allow us to do this new experiment from Russia, and that's a big step. But back in the 70s, they didn't give up. They realized that this same concept, although it wouldn't be very good in a simple mirror, if they put one on each end of a very long solenoid and then made this long solenoid as long as needed to get a lot of extra energy out, you could build something called a tandem mirror, which had almost arbitrarily high gain. And so we could be producing 20 times as much power as we required to keep the device on. And the devices look quite complicated. So you can see here are these funny shaped coils, a long central solenoid. And they actually built one of these. It was completed in 1986. It was turned on, the magnets were turned on, and then the program was terminated. And it was terminated in part because the tokamaks were in the ascendancy. They didn't quite have everything figured out, and I think it's a shame that we didn't do more experiments with it, but it is what it is. And so I'm going to use this only to show you how quickly things evolved at that time. Within 2 years of inventing the concept, they had validated it. They had moved up to the left further, and then within 6 years, they had built a reactor scale device. And that's because the system is so much simpler to build than a torus. Okay, and so this is where we're going. These scientific breakthroughs allow us to build simple axisymmetric mirrors, and we have an aspirational first step called WAM 1.0, which is the experiment I showed you. And Realta Fusion is now designing a break-even class device, which would be close to which would essentially have break-even like conditions. But further, we're going to eventually take on the tandem, and the tandem mirror you can think about. So here's our simple mirror that I showed you. You can imagine breaking it up in the middle, building 2 of those, one at each end, and putting a solenoid in the middle, and now making plasmas that stream into the central solenoid. That's where most of the fusion happens. We would have a blanket around that's breeding the tritium, extracting the heat, and making power from that. And the heat could be used for making electricity, but it can also be used for other things. So why are we doing this? I think I said that already. One of the important things is even today, we're still trying to replace something like, of our global world energy supply, 81% is still fossil fuels that we're using. And of that, if you break up that fossil fuels into areas where it's used. About a quarter of it's used for transportation. About a quarter of it's used for heating, homes in Wisconsin, and about half of it is used for industrial heat production. And so this is the biggest chunk of fossil fuels, and we should be using that energy, the heat, if you will, for making things. And so about 2/3 of this process heat, about 2/3 of the fossil fuels are used for process heat. And so we have some applications in mind for this concept. We'd like to go after process heat markets. Here is what it takes to here's a set of things that you could make, ranging from glass and cement production up around 1200 C, petrochemicals, making plastics essentially, aluminum recycling, and even fertilizer production. These are all things that require heat at about several hundred degrees Celsius, between 200 and 800 degrees Celsius. And this is sort of the range of energy temperatures where we could imagine a blanket from a fusion reactor coming out. And so this is a huge market, and this is what we're targeting with Realta. But there are other very interesting near-term applications. And so the WAM++, the device that we're building next, the simple mirror, it can be used as a neutron source which can do a lot of things. So one thing it could do, for example, is it could make isotopes at industrial scales. Rather than medical isotopes, you could make isotopes which are used for other things, like parts that are needed for space applications. And you might also imagine that we could build a microscale reactor with this, which would be several tens of megawatts rather than hundreds of megawatts. The simple mirror extrapolates to a reactor that doesn't have a low cost of electricity, but it can have a very low power size. And so, so here in Wisconsin, we have the Shine facility. It's making something like 10 to the 13 neutrons per second in each of their devices. And we'll be able to make something like 10 to the 17 neutrons per second. So that's 10,000 times as many products, if you will, if you're making them. And so in summary, I ended a little bit early. We think fusion's Kitty Hawk moments arrived. It's a form of nuclear energy, but without the downsides of fission, I would say. It's abundant. We'd like to work on industrial heat processes as our primary application. And we have a high field compact mirror approach that should be much simpler and faster than the toroidal approaches which are being used. So I think I'll stop there. I have some extra slides if we want to go into them, but it's maybe a good place to stop.
Thank you. Any questions from the audience?
Professor Forest, thank you for that most energizing discussion.
Thank you.
I can't get solar at my house because of my neighbor's trees, but I really want to go green. What does it cost to get a WAM++ in my garage? Thank you.
That's a great question. So something I didn't speak too much about is the landscape within government right now. The DOE has just started a milestone reimbursement program similar to what NASA used to develop commercial space systems. And so last fall we went through the exercise of costing out the development to get a WAM++ built, and we think it's going to be under 200 million. To be able to at least do the prototype experiments that show it works. And so that's probably short of a operating fusion reactor. It would probably be a short pulse demonstration, maybe tritium, that is the real fuel, and then to take it to the next step, if we can demonstrate the performance, we think would be straightforward, but under $1 billion.
Good talk. Thank you. Fusion is usually considered to be always 5 years ahead. I noticed yours.
20
is-
years.
Oh, yeah. Okay. It's a lot like hydrogen. It's always like 5 years ahead.
Yeah.
So I noticed you had 2030s on there. What is your really realistic notion of when we might get like the nth one where the costs are as low as they're going to be?
Yeah, that's really important because you don't really know the cost until you've built many of them, and that's important. So, roughly speaking, I mean, I'll just show you a timeline. This is notional. We're funded to build WAM 1.0, which is this prototype experiment under construction, and we're now going into the design phase, which involves a lot of theory, and so. A lot of working with computers to validate the approach, project forward, design the magnets that we think we can build, and do a proper costing. So before we ask the investors for the actual amount that we need, we have to have a reasonable costing exercise. So Realta's now going into that phase. The costing estimate is a really important part of the next step. So nonetheless, given our experience on WAM, we have some ways of scaling that up. We have some ideas about how quickly we might be able to move, and we think we could have a design, a preliminary engineering design in 2 years, and be ready to go into construction for the magnets, with the first plasma being 3 years after that. And we think that's possible because we only need 2 really strong magnets, and the heating systems are more or less straightforward to assemble.
We had a couple questions online. Is small fusion a distributed versus large central power plant? If so, what does that imply about the electrical infrastructure to deliver the energy?
Yeah, so there is WAM++ could be a microscale reactor that's producing 5 to 10 megawatts if it operates in some remote location and wouldn't need to be hooked up to the grid. It has the possibility of operating there if everything goes like we hope it will. The tandem mirror, we call it HAMMER, the high temperature superconducting axisymmetric magnetic mirror reactor. It in principle it can be scaled to whatever size we need by making the central solenoid as long as possible. And so the designs we've looked at so far have been 200 to 400 megawatts thermal. And that would be a great size to plug into, say, a aluminum recycling factory, and we wouldn't have to hook up to the grid for that. One of the reasons we're pursuing industrial heat as a first application is you don't have to hook it up to the grid, and there have been enormous delays for utilities trying to get new things hooked up to the grid, and so that's an issue for us. Nonetheless, this would probably be hooked into a grid of some sort. It's not like this can be it depends on how what the particular needs of the customer are. It gets better. It scales to lower and lower cost of electricity the bigger you get, but the capital cost for the device also gets much larger. And so we think we're hitting the sweet spot at several hundred megawatts.
Another question was, how does your device compare to that of, I think it's TAE, TAE?
Yeah, TAE is a different altogether different topology. Our system has magnetic field lines which are basically straight and open. The plasma, the field lines hit a wall somewhere. TAE is actually a torus inside a mirror, and to hold it in place requires a special set of techniques. They slam together 2 big plasmas to make the plasma hot initially, and then they hold it in place using feedback and other techniques, some of which are not different from what we're doing, but it's a fundamentally different topology.
You mentioned that there are almost 30 startup companies that are developing fusion technology. Are they all different designs, topology, or are they are part of them making products such as Commonwealth, where they're building magnets to help others? How does that field lay out?
Yeah, so I know of one company in Japan who's all about supply chain. They don't want to talk about their own fusion concept, Kyoto Fusioneering. They would like to be selling blankets and microwave sources and things like that. So that there are companies of that nature. Commonwealth Fusion Systems sometimes is referred to as a magnet company, but in fact, and that's a big part of what they do, but they also aspire to be a tokamak company, a more conventional approach. There are many startups that I know of pursuing the Stellarator, which has a number of advantages over the tokamak, but hasn't yet fully demonstrated its capabilities, including Type 1 energy, which is spun out of the UW here. There are laser fusion companies that have popped up. There are spherical tokamak companies that have popped up. There are a bunch.
Question online was, which other technologies do you think has the fastest timeline to be commercially used?
Yeah, I'm very impressed with the timelines of Zap Energy. If you ask me, who's really moving fast, there's a company in Seattle that has a system that's even simpler than ours, and it just involves making an arc in a deuterium gas and tritium gas, and they've demonstrated some they've met some very nice milestones. It's going to be a challenge to take that as far as they hope to go, and I'm looking forward to seeing what they do. Yeah.
Is there any activity still from the Russian groups that were kind of inspiring what you're doing?
Yeah, yeah. They're certainly still quite active, and they're publishing, and they're collaborating with the Chinese, which makes it even harder to work with them. And yet we have close friends, and I've been in communication with them. Initially we had a big vision of joining forces, and maybe there will still be some of those my Russian colleagues, Tavares, coming to work with us. I don't know. I haven't heard as much as I'd like to, but I know I'm staying abreast of the results. It's hard to say. I mean, their economy is now in really tough shape, and I've been told that they can't operate the GDT experiment because other things are more important. Right, Ray.
Good talk. The emphasis on industrial heat is a new twist for the fusion community, which I think is fascinating, and that's cool. Can you comment, or do you have any thoughts on how having that emphasis accelerates to commercialization of the fusion process, accelerates the whole thing into the market? And then secondly, is there anybody else with that kind of focus? This is really quite new.
Fair enough.
Yeah.
Yeah. So in fact, I think it's we went through a lot of discovery interviews during the early phase, talking to partners, potential customers going forward, and I think that's a unique thing that business brings to the fusion game. The real reason we think this is a good direction to go is because there are big energy companies that would like to get rid of their phase one emissions to make plastics, and so you have a petroleum cracker that needs a 0.5 gigawatt thermal, and they have big capital budgets. They have the timeline for the most recent cracker that was built in Pennsylvania. It was a 15-year project from beginning to end, so they have time scales. They can think about this on longer time scales. And they might have the ability to plug into it without having to plug into the grid. And so if you had to choose a partner like ExxonMobil or a bankrupt Northern California utility, it might be much easier to get a fusion reactor built in a place like this. And so the main goal is to make plant number one so that we can show that it works. And that's sort of where things have fallen down, I think. So the other thing is that so far, I think we're unique in the fusion space. I would be prized if we remain unique, because obviously if you can make heat, you can do lots of things. All of the fusion concepts and fission concepts also are working very hard on making blankets, the heat exchange fluid, as high of a temperature as you can manage, because Carnot efficiency for generators goes up, but also because the applications for manufacturing there are more of them at higher temperatures. So it's certainly being looked at in fission. We too would like to have a high temperature blanket and focus on high temperature blankets. And once we're doing that, it becomes obvious that you can plug into an environment like that.
Is there a difference between the industrial applications of when you would need to plug into the grid or not need to plug into the grid?
No. We can do many things with heat. We can make hydrogen. We can be part of an electricity system that's based on hydrogen. With heat, we can make electricity by sending it through a turbine. With heat, we can recycle aluminum cans. So we can do almost. We need the heat. We make the heat. That's our primary product. And so hooking up to the grid takes a lot longer because regulations and utilities and other things like that come into play. And there's also, there are the questions of the social acceptance for fusion. We have to work on that. It's not possible to just plop down a fusion reactor in the middle of Madison without some serious discussion. Yeah.
Yes. What kinds of companies are investing in process related fusion?
In fusion or in process heat?
Fusion as applies to process heat. Does that make sense?
Yeah, I can't tell you that. Because I only know of one company that's pursuing this, so we have investors that we're working closely with. But I would say that most of the companies which have a climate tech focus are fully aware of the importance of process heat. And Bill Gates is extremely aware of process heat as something that he'd like to invest in. So that's in part why they're pursuing fission also. And so the investors get it. They said, yeah, that's a good place to go for a first customer. Right.
We got I think pretty technical question online.
Oh, I'm ready.
What is could you speak to your efforts on stabilization methods for ballooning and lost cone drift in asymmetric geometry?
In asymmetric geometry or symmetric?
Oh, no. Oh,
axisymmetric geometry. Sure. I'm not sure it's appropriate for this audience necessarily, but the principal problems with the axisymmetric geometry are that I can show you. Yeah, so this is a really heroic simulation that took place at Los Alamos National Lab. So they packed some 100 trillion particles into a computer and started to follow their orbits. And in the simple axisymmetric geometry that we're working with, this is what happens. You can see this turbulence that develops, and this turbulence destroys the confinement, just like you might imagine. It takes the particles from the inside and puts them on the outside. Everything gets turned over. It's really bad. And this is a particularly fast instability. It happens very quickly. It's very robust in these geometries, and it needs to be dealt with. And so we've learned a couple of things. One is that if you make the ions just hotter, the simulation on the left is with the cold ions, and the simulation on the right is with the hot ions that we'll have in our configuration. This is something that relies on the extra viscosity that the fast ions give compared to the cold ions. And this extra viscosity just slows things down so that most of what you see in turbulence disappears. There's still a wobble, and this wobble We believe we can stabilize both by using external electrodes on the surface and feedback, fly-by-wire technologies to push back to keep it in place. And so this instability is relatively straightforward. This is what the Russians demonstrated. And so we think that there's already a proof. We need to replicate it here in a slightly different geometry, but the worst instability is something that can be addressed. This, by the way, is why in the early days they use these baseball-shaped coils. If you do it in that geometry, this just isn't there. Okay, so it's a great question. It's the most important question. The second thing is that, and it's even more technical. And if the questioner would like to ask me about that later, I'd be happy to jump in. There are good solutions to that. The same instabilities that were, I can say it this way. Back in the day, they discovered how to solve the drift loss cone instability by injecting plasma into the simple mirror in a certain way. And recently, the Russian experiment has also demonstrated a way of filling the loss cone so it becomes stable.
Okay, well, if there are no more questions from the audience, there's
there's
one
one more.
more.
Hello, thank you very much for this wonderful talk.
Thanks.
One thing that just like struck me as really similar to some other physics concept I know was like how you have the symmetrical mirrors is very similar to how like lasers generate their photon stimulation. Is there any like plasma based lasers? Is there any like similarities to that?
You mean with the inertial confinement? No.
With the like with a laser system that has a charged plasma, the mirrors can bounce the photons back and forth. It just had a kind of an interesting similarity to that. So I wasn't sure if there was any.
I'm not aware of any, but I'll think about that.
Okay, cool.
Okay, yeah.
Well, thank you very much for this wonderful talk. And yeah, the industrial heat aspect was very interesting as well. Thank you.
Thank you. Thank you.
Well, thanks for closing it off for me. That worked out well. All right, let's thank our speaker and thank you everyone for joining.
Thank you. Was it okay?